Our first speaker today is Professor M Jagadesh Kumar. It's my pleasure to introduce him. Professor Jagadesh Kumar obtained his master's and doctoral degrees in electrical engineering from Indian Institute of Technology, Madras. He spent the period from 1991 to 1994 doing postdoctoral research with Professor David Rulston at University of Waterloo, Canada.
I would like to thank you for inviting me to give this talk here. I work in the area of nanoelectronics, and this is what I am going to talk in the next 35 to 40 minutes or so. I will present some of the fundamental limits and the problems that are faced in building better computing systems, and then we will look at some of the alternate technologies that are available and that are emerging in order to take the silicon technology further. And then I will also look at some of the applications. I will, of course, during the course of this talk, I will be answering some of these questions that you are seeing there. Whether we can replace the existing silicon devices by the nanowire based devices, whether we can avoid using the expensive IC fabrication techniques that we currently use, whether we can replace them using cheaper and better technologies. So these are some of the questions that I am going to examine during the talk. However, just to get you motivated in my talk, I will show you a couple of slides to tell you how the present technology is changing very, very fast. Here somebody is saying, "Hello Bob, it's your father again. I have another question about my new computer. Can I tape a movie from cable TV, then fax it from my VCR to my CD-ROM, then email it to my brother's cellular phone so he can make a copy on his neighbor's camcorder?" The technology is changing very, very fast, and it is also affecting the way we are leading our lives. Another picture shows you how the way we interact with each other is also being affected. Here he says, "Dear Andy, how have you been? Your mother and I are fine. We miss you. Please sign off your computer and come downstairs for something to be loud." So this is how technology is affecting us. If you think only people who use computers are affected, even ordinary people like these saints are affected by technology. Here he says, "Blame it on the materialistic life I had, but whenever I meditate on the secrets of longevity, I can't think beyond lithium polymer rechargeable batteries." So this is how we are being affected, and who has brought us to this state? It is our penchant to make everything small and small. So that has brought us to this status. And you can see the early 1960s IC picture here, and we are making the size of these devices extremely small. I'll show you a beautiful picture of a nano flower made of indium phosphide nanowires. So we want to make everything small and small. So to what extent can we make these smaller and better? This is the picture of a ridiculously small cell phone. So we want to make everything very, very small, and when we want to make everything very, very small, we use a parameter known as feature size. So as the feature size is shown here on the y-axis and the time scale is shown here, we are here somewhere 2007 to 2010. Currently the silicon technology uses a feature size of the order of 32 nanometers. And we are moving to 22 nanometers, and we want to go further down and down. Now, why do you want to make these smaller and smaller devices? So that we can pack a large number of devices within a given die area, so that you can put more functions into a given die area. And this is a very well-known Moore's law, which tells us that the complexity of these devices is doubling for every approximately 18 months or so. Now, while the complexity of the integrated circuits is increasing, Here I have shown another picture. This is a prediction from TRS. The number of atoms that you use per bit has drastically come down. Earlier we were using bulk materials, and you can see that you have to use large number of atoms to store a bit of information. But by about 2035, we will be using only one atom to store one bit. So the size and the level of complexity of these systems is increasing. And what is the effect of all this reduction in the size? Well, as the number of transistors are packed, more and more transistors are packed per die, the cost of the transistors also is coming down. In fact, now you can, this is an old figure, now you can buy one transistor for $1 nano. So everything is now in nano. So things are becoming very, very cheaper as the device dimensions are becoming smaller and smaller. So, but however, when you make things very, very, very small, there are problems. There are problems in building better computing systems. These problems arise because of this elusive good electronic device. The electronic devices, unless they satisfy these conditions, they are not good electronic devices. For example, I must have a good driving capability. I have a long interconnection network on my chip. If I have to send a signal from point A to point B, my device has to send out good amount of current. But when the device dimension becomes smaller, the current also becomes smaller. So you must have a good separation between on and off. That is the only way to reduce the power dissipation in your integrated circuits. Therefore, one of the major challenges today in building better computing systems is the power management. There is a huge requirement for running your computers because the electronic devices that you use are not ideal devices. I have shown here some trends for the supercomputers here. The performance is shown here on the y-axis and the time scale is shown here. The red line shows the performance. As you can see, initially there was almost an exponential improvement in the performance, but now there is a kind of saturation. The performance of the computers is not increasing in terms of their number of operations they perform. However, the power dissipation, the power consumed by these computers is increasing exponentially. I have shown here some of the typical supercomputers, IBM Blue Gene, for example, and there are various other supercomputers I have shown here. And it is expected that by about 2010 also, you will reach the power requirement is of the order of 300 kilowatts. It's a huge power. You require only about 100 kilowatts or so to run a metro train. So if you want to build a supercomputer, you also have to build a huge power station next to the supercomputer. So therefore, power is becoming a major problem. If you think supercomputers are the only ones suffering from the power, even the desktop computers, the power required by the desktop computers is shown here as a function of the generation of the technology. You can see that this green line shows the dynamic power and the blue line shows the static power. Static power means when you are doing nothing on your computer, it is just idle, it is still consuming huge amount of power because of huge leakage current. And you see that as the technology is improving, unfortunately the power dissipation also is going up. So soon a laptop may consume of the order of about 1000 watts. That's a huge power requirement. So therefore, reducing the power consumption in computers has become a major problem. Now the other bottleneck is the interconnects themselves. As you might have seen, the clock speeds of the computers have not changed in the last few years or so. They are almost static around 3 gigahertz. And this comes, although your intrinsic devices can work very, very fast, your computing systems work slower because of the problems associated with interconnects. And these interconnects are made of metals, and these metals have a grainy structure like this. And this is the cross section of the different levels of the metal layers in an integrated circuit. When you scale down your devices, you also have to scale down the interconnects. But unfortunately, when you scale down the cross section of these interconnects, the resistance associated with the interconnect goes up. And as a result, you see that as the process technology is improving from 90 nanometers to 32 nanometers, the RC delay delays are going up. Even if you use copper interconnects, copper is a very difficult metal to etch, very difficult metal to handle. IBM has introduced copper as a possible material for interconnects. Even if you use copper interconnect, the RC delay time constants are going up. So this is a major problem. The third one is, of course, when you scale down everything, even your gate oxide material is scaled down. So you have huge tunneling currents passing through the gate oxide. So you have to look for alternate materials. And the transistors that you use they are three-dimensional structures, and three-dimensional structures are totally unsuitable for future computers. So we have to look at one-dimensional structures. I'll show you why we need one-dimensional structures. See, this is a transistor that we used. A MOSFET is the basic building block of any computer. And this is a 3D structure. And about 10 to 15 years ago, we shifted over to two-dimensional structures. And now people are thinking about building these transistors using one-dimensional structures, which are nanowires. So this has only one dimension, only the length dimension. So if I compress that also, then I have a zero-dimensional structure, which you call as the quantum dots. Now, the other problem that we face in building better computing system, it has reached almost a crisis situation, is the photolithography. When you define the features on a silicon surface, you use what is known as photolithography, and I have shown here that how the line width is decreasing as we move from one technology to the another technology. So the minimum feature size is the width that you can realize using your existing photolithography systems. Now, if I had to, let us say, define a feature as I have shown here on a silicon wafer, and if I am using the conventional optical lithography, then obviously if the wavelength of the light that I am using is comparable to the feature size itself, then when I am trying to define this on my silicon wafer, this is what I will get. So this is a major problem, and that is why we are unable to push the silicon technology further because of the limitation associated with the photolithography. Now, one more problem associated with the conventional CMOS technology, silicon technology, is the cost associated with these lithography systems. As I have shown here the time scale, you see by 2010 or so, the cost of the photolithography systems is going up. In fact, when you fabricate a wafer, 30% of the cost comes only from the photolithography related processing. So photolithography is a very, very crucial aspect in pushing the silicon technology further. The third one is the factory costs are going up. I have shown here the trends in the factory costs. Today, if I had to set up a silicon foundry in India, it costs about $2 billion US. The equivalent of that is about 10,000 crores. So the cost of the fabrication facilities are going up almost exponentially. Now, therefore, we have to look at alternatives. Can we bypass these expensive systems? Can we bypass the conventional photolithography and then still build efficient and fast computers? So that is what we are going to see. So therefore, people are now thinking, is there some other alternative beyond the conventional CMOS? There are, of course, options. We have spin-based devices, we have molecular electronics, and there are other options. So I am going to discuss these other options. What are these other options in order to build efficient computing systems using low-cost methods? Well, one of the things that was that is being studied is the nanowire itself. There was a lot of hype associated with carbon nanotubes. About 20 years ago, when carbon nanotubes came into picture, people thought we will build very good electronic systems using carbon nanotubes. Some people from NASA even suggested that we can build a kind of ladder from Earth to elsewhere into space so that we can transport people, because carbon nanotubes have excellent mechanical properties too. But however, carbon nanotubes are difficult to control. Their electronic properties are difficult to control. They are difficult to dope. So therefore, 10 years or so ago, people have started looking at alternatives to carbon nanotubes. And this alternative has emerged as the semiconductor nanowire. nanowires are much easier to make, much easier to control compared to carbon nanotubes. So I am going to say, I am going to look at some of the interesting work that is being done using nanowires. Well, why do I have to use nanowires in order to make these future computing systems? I have listed here some of the advantages of the nanowires. See, nanowires can be made using the well-known semiconductors, silicon, germanium, and any other compound semiconductors whose properties are well-known to us. And you can use it both as a wiring material and also for making very, very interesting devices. And since it's a nanowire, you can have a gate, a controlling gate all around this nanowire so that you can effectively control the current that is passing from one end to the other end. So that you can build near ideal electronic devices using these nanowires. So there are various methods for making these nanowires. You can very, very precisely control the composition of these nanowires. You can control the length, diameter of these nanowires. And you can also fabricate millions of these nanowires within few minutes. Whereas if you were to fabricate a silicon wafer, it takes several days of processing. And you can also combine these nanowires to make different kinds of building blocks required for making the future computers. Have anybody demonstrated any devices based on these nanowires? Well, people have already demonstrated that the basic building blocks required for making any electronic circuit can be made using these nanowires. And people have also demonstrated that they can be used as interconnects in nanoscale integrated circuits. So there are various applications using these nanowires. So in my rest of the talk, I am going to look at some of the opportunities that exist in building better electronic systems using nanowires. You can very easily control the length and the diameter of the nanowires using very, very simple methods. You can grow heterostructures using nanowires. It is very, very difficult to grow, for example, indium phosphide on silicon. But here you can change the material properties as I grow the silicon nanowire. So these kind of structures are called axial heterostructures. You can also have radial heterostructures, which are very, very useful in making optoelectronic devices. So there are various kinds of names associated with these nanowires. The kind of name that people will tell depends on the kind of researcher you are asking. But however, they are known as whiskers, nano-whiskers, nanofibers. There are a picture of the nanowires array is shown here. Typically they are called wires or nanowires if the diameter, the length to the diameter aspect ratio is greater than 20. So for example, I have shown here the picture of a nanowire which are very, very long, which can be several microns long, while the diameter is only few tenths of nanometers. They are also known as nanorods if the aspect ratio is less than 20. I have shown the picture of the nanorods here. You can also use the nanowires in order to make contacts between predefined electrodes. So these kind of structures are called nano contacts. How do you make these nanowires? If you want to make a computing system using very, very simple methods by bypassing the existing photolithography techniques, so how do I make it? One approach is you can still use the existing CMOS technology, which is known as the top-down approach, in order to make your nanowires. But then you will have to use the optical or electron beam lithography to make these nanowires. But we don't want to use this because it is very, very expensive. The other way is to use the bottom-up approach. So in this bottom-up approach, you use simple chemical methods in order to synthesize these silicon nanowires. In a conventional way, for example, you use in a top-down approach, you can define a nanowire on a silicon substrate using the existing photolithography methods. But if you want to use the bottom-up approach, you grow the nanowires elsewhere and then you bring them and you assemble them on a substrate in order to build your devices. But if you want to do this, If I have a bunch of nanowires like this, and if I want to build an electronic circuit using these nanowires, I'll have to pick one nanowire at one time and then build my electronic circuit. That is going to be extremely difficult. It is going to be extremely expensive. That is how we built 50 years ago the transistors, the original bipolar transistors. One by one we built. So things were very, very expensive, unreliable. So we want to use bottom-up approach, but we don't want to pick and place these transistors. We want to grow them. We want to self-assemble these nanowires in order to build the electronic devices. So there is one more thing that is very, very important. When we want to combine the photonics with the existing electronics, it is important that we combine the compound semiconductor devices with your conventional CMOS technology. But it is very, very difficult because you cannot grow compound semiconductor devices on a silicon wafer because of the lattice mismatch, and that will create huge dislocations and your devices will not work. And there is also difference in the thermal expansion of these materials, so it can create stress. I have shown an example of how stress can deform the materials, and that will again create defects in your circuits. So therefore, if you use the conventional technology, CMOS technology, it is extremely difficult to grow 3-5 compounds on the silicon wafer. You will not be able to get good devices. However, if you use nanowires, because they are very, very small dimensional structures, it is possible to grow heterostructures on silicon wafer using nanowires. Well, we need 3-5 compounds on silicon for these reasons. We want to put these photonics or optical devices on our silicon chips, and there is a huge market for these optical devices. So if we can combine electronics with photonics, there is a huge potential for these kind of systems. This is an example of a very, very recent example of how you can actually grow these 3-5 compounds on silicon wafer and then build lasers on a silicon wafer. You can, by changing the composition of the nanowires, you can change the band gap of these nanowires, and then you can get different kinds of lasers. There are various kinds of making these nanowires. If you don't want to use photolithography, but you want to produce this on a mass, on a large scale, you want to produce these nanowires in order to make your circuits, there are alternate methods. One of these class of methods are called the spontaneous growth methods. So in spontaneous growth methods, among these that I have listed, the VLS method is the most famous method, which is currently being used extensively. Although this method came sometime in 1960s, this has become very popular around 1998 when Charles Lieber from Harvard University has combined this VLS with other growth methods in order to make the nanowires. Charles Lieber and myself, we brought out a special issue on nanowires in November 2008 on nanowire electronics. The other kind of methods for making the nanowires are called the template-based synthesis. We'll very briefly look at these two methods and see how we can use these methods to make interesting electronic devices. So in the case of the VLS method, vapor liquid solid mechanism, you create a vapor of silicon, maybe by laser ablation, and this vapor comes into a chamber, and you have a catalyst metal put on top of this silicon surface. It could be gold or it could be iron, and when this silicon vapor comes in contact with this catalyst, these silicon atoms will reach the interface between this catalyst and the silicon surface here, and the growth starts at the interface. And you can grow extremely controllable nanowires on top of the silicon wafers. Here I have shown a better picture of how this silicon nanowire growth takes place in VLS. You have the metal droplet here, and the silicon atoms from the vapor will come and reach the interface, and the silicon nanowire grows here. As more silicon atoms come from the vapor, either from the sideways or from the top, the silicon nanowire will keep growing, and you can grow several microns length of the silicon nanowires, and you can grow millions of these nanowires in a given area on top of the silicon wafer. This is the picture of a single nanowire. This is the gold droplet that is present here, and this is only few. This length is 20 nanometers, so the diameter of the silicon nanowire is 20 nanometers. While you can grow silicon nanowires on top of a substrate vertically, you can also grow them horizontally. I have shown here the picture. If you can put the gold droplet here on the side wall of the silicon here, using the same VLS method, you can actually grow silicon wire horizontally. You can see here thousands of silicon nanowires being grown, and these kind of silicon nanowires are called nanowire bridges, and they have excellent properties as interconnects. I have shown here the IV characteristics of a single silicon bridge, and it has excellent linear properties, and if I use bundles of these silicon nanowires, I can reduce the resistance of these bundles and use them as interconnects. So this is another picture of how I can grow massively parallel interconnects on silicon substrates. These are prefabricated vertical silicon nanowires, and then you can horizontally grow the silicon nanowires in order to connect these vertical silicon nanowires. And this is another picture which shows hundreds of these nanowires grown horizontally in order to connect these vertical silicon nanowires.
Yes.
Yeah.
So cool. Are you able to control in some way the number of horizontal wires that you have?
Well, the number of horizontal wires that you have depends on the presence of the catalyst on that surface. So how well you can control in putting these catalysts here will decide the growth of these nanowires horizontally.
So you can envision patterns?
Yes, yes. You can have quantum size patterns of these gold catalysts deposited on the side walls, and from where the nanowires will grow. But of course, you have to make sure that when you deposit these quantum size gold droplets, they should not combine with each other and then become a bigger droplet. So in order to do that, you actually coat, or you put this entire thing in long chain polymer environment, so that these long chain polymers will keep away these gold droplets, right? So that is very important here. So when I use these nanowires as interconnects, it's also absolutely important to know what is the specific contact resistance when this nano bridge is touching my silicon electrode here. Typically in the current CMOS technology, if I use titanium gold contacts on p-type substrates using silicon nanowires, this is the kind of contact resistance we get. But however, using this epitaxial interfacing without using any metal contacts, people have demonstrated that the contact resistance can be brought down by orders of magnitude. So it is not just only the resistance of the wire, even the contact resistance which is very, very important. And these are very, very recent results. Sometime in July they have demonstrated. Well, it has very important advantages. That is why VLS has become a sought after method for growing these nanowires. You can control the uniformity of these nanowires, and you can grow single crystal nanowires using this method. The other method is oxide assisted growth of silicon nanowires. So in the previous method, you need either iron or gold as a catalyst to grow the nanowires, and gold is a contamination, it's a contaminant in silicon fabrication. So if you want to avoid any metal contaminants, the other way is to grow silicon nanowires using just silicon oxide powder. If you have silicon oxide powder and if you heat it, the unbonded silicon atoms in the silicon oxide powder, they react with the silicon substrate here, and the growth starts here. As the silicon wire grows, the oxygen atoms are pulled out, and you will have here an oxide layer also being grown on top of the silicon wire. So this is also another method that is currently being used for growing the nanowires. The biggest advantage of this method is that there are no contaminants if you use this. The template method is used to make nanowires. Here in this case, you actually create pores inside, for example, anodized aluminum oxide, which is known as AAO. And you can then fill up these nanopores using various techniques. There are various techniques available to fill up these nanopores. And once you fill up these nanopores, you can remove this material, you can etch out this material, and then you have the vertical nanowires on top of a substrate. You can then transfer these nanowires to any other substrate in order to make your devices. This is the picture of a closer picture of a nanowire template, and the diameter of these pores can vary from anywhere tens of nanometers to hundreds of nanometers. And this is a picture of how the nanowires can be formed using these templates. You have a method known as electrical field directed assembly, because these nanowires can be charged by applying an electric field, and then they can be aligned. And this method is called the electric field directed assembly. The advantage of this is that you can have one layer of nanowires aligned in one direction and then change the substrate by 90 degrees and then align the nanowires in the other direction. So therefore, you can actually build these nanowires layer by layer. I have here an example of, this is from Charles Lieber's work, which he has published some time ago. You have here two electrodes, and you put a droplet of these nanowires. This liquid contains the nanowires, and you apply a combination of the DC voltage and AC voltage, and then you align these nanowires here between these two electrodes. So you can see that you can actually have two nanowires at 90 degrees to each other, and when these nanowires touch each other, there is a junction, and this junction can be used to make your electronic devices. Other method that is being used is called the flow directed assembly. So you have here a tunnel kind of thing created on top of the substrate, and you put the liquid containing the nanowires, and when you increase the pressure of this liquid, the nanowires will get aligned. And here you also have to ensure that the nanowires, once they stick to each other, it's impossible to remove them, separate them. So therefore you have to add some polymer materials in this liquid, so that when you apply pressure, they don't join each other, they still remain isolated from each other. And once you have these aligned nanowires on top of the a layer of material, it could be a plastic material, and then you can transfer them onto your substrate and change the direction of the substrate and grow the nanowires in the opposite direction, so that you can have crossed arrays of these nanowires. These cross links are known as Lieber arrays after Charles Lieber, and these are being tested out in order to build efficient memory systems. So this is an example of how the microfluidic flow will cause these nanowires to be aligned, and then you can build these devices using this crossed wire array. These are some of the properties of this crossed wire array. If these nanowires touch each other, there is a p-n junction formed. During the growth of these nanowires, you can dope them very precisely, either to be p-type or n-type. And these are the characteristics of this nanowire made of indium phosphide. So that is why you see that they start conducting at a larger forward voltage here. So between these two nodes, you have a linear characteristic. Between these two nodes, you have a linear characteristic. But when you check between these two nodes, you will get a p-n junction characteristic. A p-n junction is a building block for any electronic device. Now, if you build these p-n junctions or electronic devices, what kind of impact it will have on future integrated circuits? there are a couple of things that we have to keep in our mind. If these nanowires have to make any impact at all, what is that we have to look for in the properties of these nanowires? In the last few years, the wafer size has not really increased. We are stuck to around 18-inch size wafers. You can't really go beyond that. And the die size also has remained at around 100 millimeter square. So, and we have also almost reached in terms of our the cleverness in designing these circuits. So we have almost reached a saturation point. Now, if you want to further push the silicon technology beyond this point, if you use the conventional devices in order to push your silicon roadmap, it's going to be extremely difficult. The device that we use in today's CMOS technology is known as the FinFET. A FinFET consists of a silicon fin here, which is 5 nanometers in width, maybe tens of nanometers in height, and then you have a gate all around this fin. So because the gate is all around, you can effectively control the current flow from the source and drain. And if I had to use nanowires, and if I had to take these nanowires as a replacement for these existing FinFETs, the nanowires must satisfy certain conditions. Whether we will be able to do that, it's not yet clear. Suppose I am making my existing systems using FinFET based MOSFETs. I have shown here the dimensions of the fin for a typical MOSFET. It has a width d and it has a height h, and there is a pitch, that is the minimum distance that we have to maintain between these two fins. So I have the gate material all around this fin. Now the net gate width is the entire length, which is 2h plus d. If I had to pack too many of these FinFETs on the surface of the silicon wafer, then obviously the 2h plus d has to be much greater than this w. That is, I had to pack these FinFETs much closer. And it is a possibility. We can actually do that using the existing photolithography techniques. But however, if I use a nanowire in order to make a MOSFET, the nanowire is lying on top of this silicon substrate, and the diameter of the nanowire is d, and you have the gate oxide and the gate material. So if I call the gate oxide as Tox and the gate material thickness as Tg, and if the diameter is d, the total pitch that is required for the nanowire is d plus 2 times Tox plus Tg. So this must be smaller than w. If I had to put these nanowires closer, so this entire length has to be smaller than w. Or in other words, the entire length, which is pi d, that has to be greater than w, which is going to be very difficult, because the d, the diameter of the wire, has to be greater than the 2 times Tox plus Tg divided by pi minus 1. If I use my conventional technology, if my oxide thickness is about 5 nanometers, if I am using high K dielectric, and if my poly thickness is about 5 nanometers, that means the diameter of the wire has to be greater than 10 nanometers. Whereas we are planning to use nanowires in order to have a better characteristic for our devices, the nanowire diameter is of the order of 3 nanometers, 4 nanometers, 2 nanometers. On the other hand, if I had to build an integrated circuit using these nanowires, the d has to be greater than 10 nanometers. So there is a problem in using horizontally laid nanowires if I had to build efficient, highly packed integrated circuits. So in order to overcome this problem, what we need to do is build these nanowires vertically. Don't lay them horizontally on top of the silicon surface. And you can also use these vertical transistors not only to pack these transistors very close to each other, you can also use them as pass transistors between different layers of these metals on your integrated circuit. So therefore now there is a lot of interest in making vertical nanowire transistors rather than horizontal nanowire transistors. This is a very recent example of the vertical nanowire transistors. I will not go through these details, but using the conventional CMOS technology, it is now possible to build vertical nanowire transistors. These are the examples of the TEM pictures of the vertical nanowires. You can actually build an array of these vertical nanowires, and around these nanowires you can grow your gate oxide, put your gate material, and build your typical MOS transistors. So these are the typical characteristics of these vertical gate all-around MOSFETs, which were reported a few months ago. Once you have these vertical nanowires, you can actually build your logic circuits. I have shown here a simple example of an inverter which can be made by simply using these vertical nanowires. This is another example of Charles Lieber's work where they have used the horizontal wires, nanowires, in order to build a simple inverter. These are the characteristics. So I have the input and an inverted output. If I use these inverters, I can also build ring oscillators. And so this is an example of how these nanowires can be used in order to build your future electronic devices. If I make the nanowires using silicon, silicon has limited mobility. Can I make these nanowires using compound semiconductors so that I take advantage of the larger mobility in these materials? So this is an example of an inverter built using compound semiconductors. So I have here to build a p-type MOSFET, zinc phosphide, and then cadmium sulfide for the N MOSFET. And using this I can build an inverter using compound semiconductors, which is not possible using conventional technology. And these are the typical inverter characteristics for these nanowire based transistors. The FinFETs themselves can be converted into nanowire based transistors. This is a very interesting work being done in Singapore, where if the FinFET is oxidized, you can grow very, very controlled nanowires by etching the oxidized fin here, and then you can grow the gate all around transistor here. This is an example of a gate all around transistor using the existing CMOS FinFET transistors. And this is a closer picture of how the fins can be converted into nanowires using the existing CMOS technology. So there are all kinds of efforts. Use the existing CMOS technology or use alternate methods in order to grow these nanowires and then make the logic circuits. These are the typical characteristics of a MOSFET made on silicon nanowires. You can, they have realized a very large on-off ratio for these silicon nanowire based transistors, which is very, very good. We wanted to have a good difference between on and off state, and that is defined by this on-off ratio. One of the recent applications of the nanowires is not only to build electronic devices, field effect transistors or diodes. Recently IBM has come up with a new memory technology known as the racetrack memory using nanowires. The conventional memory, semiconductor memories or magnetic memories, they have their own limitations. For example, if I am using these random access memory, SRAM or DRAM, these memories have to be refreshed about 1,000 times every second. That means you are consuming power in order to refresh these memories. But however, if you build memories using nanowires, Charles Lieber has shown that these nanowire based memories can retain the charge for about 20 minutes. That means you need to refresh only 3 times in a minute. For about 20 seconds it can hold the charge, so only 3 times in a minute you have to refresh. That means your power consumption for operating these memory systems will be extremely small. This racetrack memory can be built either using these horizontal wires or vertical wires, as we have seen just now that it is not efficient to build horizontal nanowire based devices. So people are looking at these vertical nanowires in order to build these nano wire based memories. In this racetrack memory, you have the a read and write mechanism at the bottom of this U bend, and nothing moves in this memory, only the magnetized domains are moved through this memory, through this nanowire, and this magnetized memory presence can be either read here or it can be written here using this read write head. These memory domains, these magnetized domains can be moved very, very fast. Therefore, it is expected that using these kind of memories, you can build extremely fast memory systems which consume very, very low power. Well, when I was a student, I know many of my colleagues who worked in conventional CMOS facilities, they have grown bald because integrated circuit technology uses extremely toxic materials. In fact, it is the most toxic industry compared to any other industries, and most of them have grown bald. This is how one will become. But however, in future, if you work with nanowires, you can very easily recognize the person who works with nanowires, well, the person who is standing there in the middle. Very briefly, I have looked at what are the existing problems associated with the conventional CMOS technology, associated with the speed and the power consumption, and then we looked at some of the alternate methods that are currently being tested in order to build extremely efficient computing systems. We do not yet know whether these nanowires will ultimately be used to build efficient computing systems, but there is a large amount of interest in using nanowires for building future computing systems. So with that, I conclude my talk.